We do science in a lot of ways. We look at the sky to see what shines steady and what flickers, flares, or moves. We run computer models to see if the physics we think is happening can reproduce the universe we see. And sometimes we even recreate the universe in the lab and try to only blow things up in intended ways. Today, we bring you all these kinds of stories as we look at how to save our planets and try to understand how Mars may once have lived and died. We also have This Week in Space History and the Japanese Selene mission to the moon. All of this and more, right here, right now on the Daily Space. I'm your host, Dr. Pamela Gay, and we're here to put science in your brain. The history of astronomy and cosmology is full of stories showing how breakthroughs often occur one laboratory experiment at a time. During the last century, laboratory researchers explored how elements emit light at specific colors when heated to different temperatures. This has allowed generations of researchers, including me, to tease out what elements compose the stars and estimate just how hot various objects may be. From experimenting with the interactions between light and atoms, researchers have moved on to exploring the relationships between energy and particles. This is accomplished in massive research facilities that can accelerate atoms to high velocities and crash them together to produce new and often unstable particles and atoms. Using Michigan State University's National Superconducting Cyclotron Laboratory, researchers have studied how a beam of a specific chlorine atom, chlorine-31, could stream into a detector and decay into sulfur-31 with a flip of a proton into a neutron. This sulfur would then, sometimes, release a proton and evolve one more time into a phosphorus-30. This work appears in Physics Review Letters and was led by T. Budner. This process, which reduces atoms from the 17-proton chlorine atom to the 15-proton phosphorus, is the inverse of a process that occurs in exploding stars and builds atoms with progressively more protons in their core. And this experiment was the first time we've been able to directly measure the rate that this kind of a reaction can occur. This experiment provides new information on how fast or slow reactions can occur, and it informs how many different kinds of atoms have a chance to form during supernovae. With this new data plugged into supernovae models, they find that the explosions of white dwarf stars rich in oxygen and neon can produce excesses of the isotope silicon-30. This stable atom is found in grains of stardust and is a building block of everything from meteorites to Earth itself. And now we know. Because atoms were slammed around in a lab on Earth, science is weird and science is awesome. One thing science sometimes isn't is straightforward. In the first half of the last century, Einstein redefined how we see our universe with his introduction of relativity. His work, which many non-scientists still somehow struggle to accept, describes interactions between mass and energy. Interactions like the orbit of the moon and the bending of light around our sun, as being a reflection of how our universe's structure is shaped by gravity. According to his theory, any two masses in a gravitational field will fall at the same rate. Astronaut David Scott demonstrated this with a hammer and feather on the moon in 1971. And today, two masses, platinum and titanium alloy test masses. Repeat this experiment in orbit around our planet with remarkable precision within the microscope mission. The reason for this experiment is to see if the tiny quantum fluctuations that permeate our reality could be seen to affect gravitational interactions. The two masses were contained within a larger sphere set orbiting our Earth, and electrostatic forces were used to see if the two masses fell around the Earth in their orbit with any differences. These measurements were accurate to 1 part in 10 to the 15, and according to a new paper in Physical Review Letters, they saw no differences. This means that while we can detect the quantum vibrations in mirrors using lasers, we don't see any similar anything with gravity. This once again seems to indicate that Einstein's geometry-based description of gravity resists being combined with the particle-based descriptions of all the other forces using quantum mechanics. I, for one, like my space-time curvy and welcome this lack of measurable quantum variations in these orbiting masses. I have to admit, I am not, and don't ever plan to be, an experimental astronomer. Give me data from a telescope and I'm happy. If you give me a telescope, I'll just attract clouds. So really, I just want the data. It is from this perspective of being an observational astronomer that I now say some experiments really feel like things we should not do even if we can. At least not yet. In a new paper in Environmental Research Communications, an international team of researchers led by Wake Smith state that it is possible to refreeze the Earth's polar regions with the injection of aerosols into just the right places in the stratosphere. These aerosols would then reflect incoming sunlight, preventing it from warming the Earth, and if done correctly, would provide a cheap and effective way to reverse some of the effects of climate change. I'm just worried about what would happen if there are factors we don't understand. So yeah, the experimentalists could cool our planet, but maybe let's not try until we've exhausted all other options. And maybe let's work on understanding how other worlds like Mars may have died before we tried to save our planet Earth. Coming up, we're going to switch to looking at other planets. Stay tuned. NASA's Curiosity rover landed on the red planet 10 years ago. Since then, it has traveled over 18 miles along the surface, trundling slowly as it gathers massive amounts of data, searching for evidence of flowing water. The landing site of the rolling laboratory is Gale Crater, an impact crater created at least 3.5 billion years ago. The crater is full of sediments, making it a prime target for understanding some of Mars's wet history, especially with Aeolus Mons, a Mount Sharp in the middle. As Curiosity approached the small mountain and started climbing its slopes, images revealed sedimentary layers in detail, likely created by water-eroded lake deposits. Mount Sharp is about 1,300 feet high, and the depositional layers represent millions to tens of millions of years worth of deposited sand and mud. Curiosity not only took images of the formations, but also collected samples of the rock and soil, which were then analyzed with the onboard instruments. With more than 700 published papers to date, scientists around the world have discovered evidence of Mars' ancient wet past, a past that could have been habitable for life. Now, in a new paper recently published in the Journal of Geophysical Research with lead author Jessica Watkins, researchers have presented evidence that water was not the only erosional force responsible for the shape of the terrain. Co-author John Gottsinger explains, quote, "The work of erosion on Mars is driven principally by the wind, which acts like a feather duster over hundreds of millions to even billions of years. This is very different from Earth, for instance, where the extreme ruggedness of the San Gabriel Mountains in Southern California is created by torrents of rainwater dissecting the landscape over relatively brief periods of geologic time. End quote. There are several distinct reasons for the difference in erosional processes between Mars and Earth. First, much of Earth's land formation is related to plate tectonics. For example, two continental plates push up against each other, such as in the Himalayas, and they cause an uplift that builds mountains. At the same time, rivers in the region continue to cut down through the rock, resulting in deep canyons and exposing rocks from past millennia. Earthquakes can bring mountain slopes down. Volcanoes can create new landmass, all as a result of tectonic processes. And although the InSight lander has detected hundreds of small Marsquakes, there is no evidence of tectonic activity. Instead, the surface of Mars is shaped by wind erosion. In addition to Mars not having plate tectonics, the atmosphere of the red planet is a mere 1% that of Earth. As a result of that massive difference, much of the planetary society community downplayed the role of wind erosion on Mars. Wind may not play much of a role in the present day, but the evidence suggests it played a pivotal role billions of years ago. As the press release explains, quote, the 300-meter thick Murray Formation, which was formed from sediments deposited by water, has been eaten away from the top down. Further, the sediments deposited on top display a cross-bedding that is indicative of ancient sand dunes marching across the desert driven by wind. On the whole, the landscape looks like a wet environment that was taken over by the Gobi Desert. End quote. By documenting the many cycles of erosion, scientists can better understand the changing environment on Mars. And as Goetzinger notes, quote, all of this helps us understand how Mars works overall and will inform scientists interpreting the observations of the Perseverance rover as well. End quote. While we wait for the Mars sample return mission to bring us rocks from Jezero crater, both Curiosity and Perseverance continue to bring us amazing science. Understanding the evolution of planets is one of the most important aspects of understanding planetary formation. We've said it before and we'll say it again. No one set of rules or processes seems to apply to the formation of planetary systems. Our sample size of 1 has been proven to be an outlier of a system so far. And with bigger and better telescopes, we are getting to the point where directly imaging exoplanets is becoming more and more common, aiding us in our quest to find patterns. Even better, we're beginning to find incredibly young planets. And a new paper in the Astrophysical Journal Letters with lead author Fiang Long has provided a potential new method to find these worlds. In this case, an exoplanet in the range of Neptune or Saturn size was discovered in the disk of planetary dust. The disk is LACA 15, about 518 light years away in the constellation of Taurus, and Feng analyzed new high-resolution data from the ALMA Observatory to detect features that point to the presence of a planet. The protoplanetary disk is about 42 astronomical units from its parent star, and dust collecting in the L4 and L5 Lagrange points of the star indicate that a planet is forming in the disk. Long explains, we're seeing that this material is not just floating around freely. It's stable and has a preference where it wants to be located based on physics and the objects involved. End quote. And the baby exoplanet is only about 1 to 3 million years old. When you find one example, you know you have the tools to find another example. Scientists are continuing to push the limits of what we know, providing us with glimpses of processes long past for our own solar system that can then be applied to exoplanet populations. Once we have even more examples to work with. And now, let's change things up with a rocket launch. And now, let's hand things over to Eric Mattis and change things up with a rocket launch.
Now, an update on the rocket launches that went up since last week. There was only one, from China. However, it's worth noting as it was only the fourth Long March 7A. The rocket sent up a satellite called ChinaSat-1E from Wenchang, China's satellite launch center on the island of Hainan. The lower latitude position gives rockets heading east more performance thanks to the Earth's rotation, and drop stages land in the ocean, not on land. Both of these qualities are useful. Let's watch the launch. ChinaSat is a series of government-owned communications satellites usually launched by the pretty but deadly hypergolic-propelled Long March 3B series of rockets. China is continuing to transition its routine launches over to its new generation of rockets, however, and this was the first ChinaSat to be launched on a Long March 7A. The 7A adds the liquid hydrogen-propelled third stage of the 3B to the kerosene-oxygen first and second stages of the Long March 7. The Long March 7 will replace several Long March rockets, including the 2F and 3B. According to an article on the manufacturer's social media, putting the payload on this new rocket was quite a bit of work, made even more complicated by working around pandemic restrictions. A link to the article in its original Chinese will be in the show notes for this episode. ChinaSat-1E will be used to deliver television, voice, and radio to users on the ground. Coming up next, we look back at an important mission in lunar exploration. Stay tuned. Last week, we talked about U.S. space policy speeches, particularly related to crewed lunar missions. This week, we have an uncrewed lunar mission from Japan, Selene, also called Kaguya. Japan's space program may have fewer resources than other countries' space programs, but they still managed to complete innovative missions. One such mission was the Selenological and Engineering Explorer, or Selene, the largest object put into orbit around the Moon since the Apollo missions in the late 1960s and 1970s. Selene's goal was to survey the Moon's surface from a very low orbit inclined 90 degrees to the equator. This orbit allowed the close study of the Moon, but required more propellant due to the lunar mass concentrations skewing its orbit. Selene launched on September 14, 2007, on an H-2A rocket from the Tanegashima Space Center in Japan and entered orbit around the Moon on October 4th. Once in its high capture orbit, Selene deployed two small satellites. The first was a relay satellite to ensure the main satellite could maintain communications with Earth while on the far side of the Moon, and the other to perform very long baseline interferometry in cooperation with radio telescopes on Earth. After the insertion of those two satellites, Selene lowered itself into its operational orbit of 100 kilometers above the Moon, where it stayed for the next 15 months until it was lowered into a 50-kilometer circular orbit. The orbit's lowest point, the periloon, was further lowered to 30 kilometers 2 months later. Finally, after Selene had exhausted most of its propellant and had a failing reaction wheel, the spacecraft was deorbited into the lunar surface on June 10, 2009. What did it do during all of those months, and what have scientists learned by analyzing the data since? Lots! Selene had 14 instruments on board and also conducted an investigation in conjunction with its two small sets. Selene's primary objective was to measure the Moon's gravity, topography, and mineral composition. It measured topography by combining pictures with data from a laser altimeter and tracking data from Earth. Gravity was also measured indirectly by tracking the spacecraft's speed in orbit from Earth. Its orbital speed changed slightly depending on the local gravity. To measure gravity on the far side, Selene used its relay satellites. Measuring the gravity of the Moon helps understand what's below the surface, which gives some clues to how it might have formed and changed. Combining these three methods, Selene discovered that the lunar far side has very different gravity concentrations than the near side. On the near side, there are more areas of stronger gravity, namely mountains. and other mass concentrations or mascons. On the far side, there are no mascons, but instead large numbers of basins and craters. The reason for this difference is thought to be a result of differential cooling, with the far side being cooler and thus more resistant to changes. Selene's measurements determined a possible age for when the geologic activity on the moon ended, 2.5 billion years ago. A paper using Selene data was published this year, 2022. Selene also mapped the entire moon in 10-meter stereo resolution. This means it had two cameras with different perspectives, one on the front of the spacecraft and the other on the back, that combined to produce three-dimensional images. Selene's mission overlapped with several other lunar orbiters, including China's Chang'e-1, launched 1 month later, and India's Chandrayaan-1, launched 10 months after that. Chang'e-1's mission ended before Selene, deliberately impacting the moon on March 1, 2009. Chang'e-1 was followed by 4 other Chang'e lunar missions later in the 2010s and 2020s, including 1 more orbiter, 2 rovers, and a sample return. NASA's Lunar Reconnaissance Orbiter, which entered lunar orbit 13 days after Selene was deliberately crashed into the surface, is still in operation today. Chandrayaan-1 is inactive, but is still in orbit around the moon. And now, for some statistics. The number of toilets in space is 8. 4 on the ISS, 1 on Soyuz MS-21, 1 on Crew Dragon Freedom, 1 on Tianhe, and 1 on Shenzhou 14. We keep track of orbital launches by launch site, also called spaceport. Here's that breakdown. USA, 53, China, 35, Russia, 7, New Zealand, 6, Kazakhstan, 5, French Guiana, 3, India, 3, Iran, 1, South Korea, 1. From those 114 launches, a total of 1,772 spacecraft have been put into orbit in 2022, with 1,350 of them being Starlinks, which is about 7 out of every 10 satellites launched so far this year. Your random space fact for this week is that astronaut and lead author Jessica Watkins made the final edits to the paper recently published about wind erosion on Mars while she was on board the International Space Station. She completed the paper as a postdoc and made it all the way through astronaut training and into space before the proofs were ready from the publisher. This has been The Daily Space. You can find more information on all our stories, including images, at dailyspace.org. As always, we're thanks to the donations of people like you. If you like our content, please consider supporting us on Patreon at patreon.com/CosmoQuestX.